to start recording. This thing does not record by itself. All right. Now, and whatever message you tend to ask regarding the course in general, send it to all the people, entire audience, instead of only to me in private, so that I don't have to read that question again to other people. All right. So is everybody clear on HDFS? Should I move on? Great, great. So everybody is familiar with HDFS. Today we'll go through a little bit more into details. All right. So the next step in any big data system, after you have made sure that you are able to store so much of data, how will we do the computation on this data efficiently? Is it possible to distribute your program onto the multiple computers so that your code runs on each individual machines having the data instead of bringing this data to centrally somewhere else? The way we had been doing our database programming, we always fetch data from database. Instead, we should be sending the code to the database. Why? Because the data is generally huge and your code is generally very, very small. A code of size 1 MB is actually considered pretty big. Okay, a logic of 1 MB, 1 megabyte is considered really huge. While data, the kind of data you handle in case of big data system, it might be in terabytes, it might be in gigabytes. So it's always economical to send the code to the data instead of data to the code. The only downside of the approach of sending code to the data is that it's generally quite complex. All right. So let's see how does Hadoop facilitates you in in doing the computation. How does it help you in doing the computation? Let's try to understand this. So, the mother of almost all the computing problems is sorting. Okay. Here we are discussing about sorting. Why? Because the sorting is okay. So, let's say sorting is okay. Yeah. All right. So the mother of almost all computing problems is sorting. And sorting means ordering the data on certain parameters. All right. And mostly considered as mother of most of the computing problems. And why is it so? Why does sorting matter to us? As an engineer or as a somebody who deals with computers, it is very important to know that sorting is something which is involved in most of the problem. Let's say when we say select star from my data, select star from my table where x equals my x1 value. This is an SQL query, right? And this SQL query is extremely slow if this column called X, this is a SQL query which looks up for the data where your column X is equivalent to X1. Imagine this, if X1 did not have an index, okay? An index is something like you have on the back of your book. If there is no index in the book, it's impossible to find a word in the book. You will have to go from left to right, searching for that particular word you are looking for, and you will end up nowhere. It might take you few hours, and same is the case with computing. If there is no index, if there is no index, if there is no index, then this query will be slow. And what is indexing? Indexing is basically a sorting. Indexing is nothing but sorting of the data to form an ordered list of things so that in an ordered list, in in an index, you can quickly search, you can quickly do a binary search. All right? So in an index, you can quickly do a binary search. The way you go back, you flip to the back side of the book, and if you're looking for a word, what you do is you just look at the top of the page, bottom of the page, and then if it is within this range, you jump into the middle of the page, and then because the index is sorted words, so you know exactly how to find it. All right. So basically, if the data is very well sorted, you can quickly find things. And therefore, a select query like this is essentially a, it is essentially a sorting problem, right? Similarly, similarly, let's take about joins. Joins. Select star from table 1, join table 2 on t1.id equals t2.id, right? Now, how come this is a how come this is a sorting problem? Do you think it's a sorting problem? Anyone? Great. So it's a sorting problem in the sense that T1's ID column and T2's ID column will be first sorted and then looked for equal value, right? If this data t1.id and t2.id, these two columns are not sorted, imagine how would it look like. Without sorting, it would be like take a value, take a value from t1, search in t2, and do this and repeat this for all values of t1. So if the if the total number of records in T1 is M and total number of records in T2 is M, total number of times you are going to look up is N into M, which is really very slow. Okay, so without sorting, this will be this kind of primitive. And you can think of it, if one comparison is taking 1 millisecond and there are 1,000 records in table 1 and 1000 records in table 2, it is going to take 10 megaseconds, all right, which might be few days, all right, which might be few days. So without sorting, the whole world of computing will be horribly slow. Now let's take a case of order by. Order by is of course blatantly is obviously sorting. Group by group by is sorting, right? So the whole SQL query, if you look at closely, is um, under the hood, it's a sorting problem, right? So if somehow we are able to figure out if we are able to figure out how to do sorting on hundreds of computers parallelly, we should be able to do any kind of data churning really fast. Okay, so it's not only SQL, even in the cases of finding path, a complex problem like finding path from one location to another location, those kind of assignments, those kind of problems also involve a lot of things. Those kind of assignment can all also benefit from sorting kind of algorithms. All right, so let me check once what is the status of my disk. All right, so the important part is that sorting is the very important problem, and we should all know that how much time we should know that how much time sorting is generally takes. All right, now let me understand how well do you understand the data, how well you understand sorting. So you have 1 gigahertz processor, okay, and you have 1 terabyte of data. And in what form is this data? Imagine a plain text file containing 10 billion names. Each is 100 characters long, or maybe there are multiple such files containing these names, such that the total is 1 terabyte. Now your duty is to sort these names using a computer which has 2 gigabyte RAM and 1 gigahertz processor. How much time do you think it will take? 10 hours. Good. Anybody else? More than 5 hours. That is Sarju. Okay. Okay. Anybody else? Just rough estimate. Even if you are wrong by 100%, which means your answer is twice what it is, it's still okay. Right. All right. Okay. Before this, let me also quiz you once again. So, Johnny, it's okay if you send it to entire audience. Once again, let me ask you another question before I move on to this. If you have a big hard disk of 1 terabyte data and you want to go through the whole hard disk, you are looking for one string and you start with one side and start scanning the whole. Okay. How much time do you think it will take you to read the whole data from 1 terabyte hard disk? Anyone? 2 hours? No. To read 1 terabyte data from your hard disk, the whole data from end to end. Okay. You're not keeping it in memory, you're just reading it from one side to another. How much time do you think it will take? Half day? Over a day? All right. So let me just do a little maths. So on an average, it takes around for 1 MB data. For 1 MB data, it takes around 20 103 103 these many nanoseconds. Okay, these many nanoseconds, which means for 1 GB it is going to take 20 seconds, and for 1 terabyte it is going to take 20 into 1024 divided by 3600, these many hours. Okay, so how much it is going to be? It is going to be something like 5 hours, 5.8 hours. All right. So, so to just read this data, it would take close to 6 hours from a hard disk. All right, just to read this data. So, right now, to me, it took around 6 hours because one of my hard drives was solid state hard drives, and one of the hard drives was normal hard drives. That's why it took me 6 hours. But I'm sure if I do it again using a normal hard drive, it might take something between 8 to 10 hours. Okay. Now, the idea was to give you a general overview of how slow is your computer. And trust me, here your processor is fairly free. It is the IOs which have taken maximum amount of time. Okay, it is the IOs which is inputs and outputs. You are reading, the maximum amount of your time went into reading from the disk. Okay, and since I parallelized the two things, while I was reading the data from the disk, I was doing I was sorting the data parallelly. So CPU was busy in sorting while the data was being read from the disk, and this basically made the whole process really fast. All right, so essentially it would take around 6 to 10 hours for sorting such data. Okay. And the earlier number of 5 hours was because I did it using SSD. I tried again, it took me more than 6, 7 hours. Okay. So depending on the circumstances, it might take something between 6 to 10 hours because every hard disk has got a different RPM, and I was using really fast hard disk. Okay. Now moving on. So what is wrong with these 6 to 10 hours? What is wrong with these 6 to 10 hours? First, it's extremely slow. If in an organization somebody tells you tell your boss that hey, to find an average on this data, it will take 6 hours. Okay, that's not going to help. Okay, just to find an average or just to find something, it is going to take 6 hours. All right. So we need a faster sorting. We need a faster mechanism of reading data, sorting it, and processing, doing other kind of computation on top of it. All right. Second is we might have bigger data than 1 terabyte. Third is we might have to do it every day. If we do it every day, is our process, whatever we have built, is sustainable? All right. So, and to give you an overview of what kind of work Google did in 2011, they sorted 10 petabyte of data, which is 1,000 times bigger than what we 10,000 times bigger than what we have just talked about, and they did it in 6.5 hours using 8,000 computers. Okay, so sorting being such a problem, the whole world keeps on competing on these sorting benchmarks. So Google and Hadoop has been the winner so far. All right. Now, so it is very clear to all of us that we require a compute engine which can do sorting on using multiple computers, which can do processing using multiple computers. Here, our processing was majorly slow for two reasons. First, we had to read a lot of data from the disk. Second, sorting requires the data twice at least. Therefore, this sorting therefore, there were two bottlenecks in our game. One was CPU and RAM. One was CPU and RAM, and second was IOs, input and output. Now, to help these kind of processing, Google came up with a MapReduce kind of architecture, and on the top of it, Hadoop guys implemented the Hadoop MapReduce. Okay, we'll go into this detail now. So similar to our HDFS, where we had a name node and we had the data nodes. Here we have a job tracker and task trackers. All right, we have job tracker and task trackers. Just a second, I'm getting some messages. All right, so there's a job tracker and there are task trackers. So job tracker is like the floor supervisor which just does the accounting on it keeps a track of who is doing what, and in case a task tracker is not working, job tracker assigns the work to somebody else. Okay, so you can think of the job tracker to be the supervisor of a shop floor. All right, and task trackers are basically the real executor of the work. So whatever code you assign give to job tracker for computation, it sends that code to each task tracker and that code gets executed. Now, your code, whatever you want to execute, you will also specify that you want to execute your code on top of this particular file. And job tracker will only send your code for the execution on the task tracker which are very close to the data node. Okay, so I've just stepped a little, jumped a little ahead. So job tracker knows about the name node, all right, and and whenever you ask job tracker to do something, you also tell job tracker that here is my file in this HDFS folder. Just I want to process this particular folder or particular file, and here is my code that will process this data. All right. Now, job tracker will ask the name node that do you know where is this data? And it'll tell job tracker that these are the data nodes containing the blocks of the file which you are trying to process. Okay, so send your work only to the task trackers which are very, very close to the data nodes. So data node is a process, task tracker is a process, job tracker is a process, and admin node is a process. Process in terms of operating system. These are the processes running on a Linux machine. It can run on Windows as well, but right, and these are basically the Java processes. Java process is nothing but a new Java virtual machine created on your computer, right? And the way you communicate with these services are mostly running, and the way you communicate with these services is by the way of talking to them via port, TCP/IP port. The way when you deliver an email, you connect to a server on 25 port. Similarly, when you are connecting to a database, you are connecting to a database or a particular IP address on a particular port, right? So port is a number, and they all have different numbers. Task tracker has a different number, data node has different number, and name node has, all right. So every time you want job tracker to do something, it goes to name node, ask about the file which you are trying to process, and then it finds the data nodes containing the blocks of that files, and then tries to find out which are the task trackers which are very busy and very free, and will schedule accordingly. That scheduling algorithm is really interesting. It tries to first figure out what is the most closest one to the data node, to the blocks which we are talking about. And in case those task trackers are busy, it sends it finds out other task tracker containing at other task trackers close to the other data nodes containing the same block, and then tries to execute the work there. All right, this is how job tracker task trackers work. Sounds good? So generally, a task tracker and data node run on the same machine, but it is fairly optional. It is not mandatory. You can have a machine running only the data node, or you can have machine running only the task tracker, or you can have a single machine running all the four things. All right? So the virtual machine you would download, or if you had downloaded already, the virtual machine contains all these components in that single computer. All right? So these are the core components, and the way it happens again is the same diagram shown in a different way. Client comes to the job tracker, tells job tracker to do things. It gives the job tracker the code it wants to execute on task trackers, and and it also tells that it wants to process these files, and job tracker takes the hint of executing the logic of client based on the files the client has specified. All right, now the same process of execution is again explained a little more in detail. So as a user, what will you be doing? First, before you want to process anything or using MapReduce, you copy those files onto HDFS. You copy those files onto HDFS. After that, you submit the job to using a client. Client is Hadoop client available on the machine as a normal binary. You as a user use that client to submit the job. Now this client uploads the job onto the HDFS. Along with that, it finds out where is the it talks to the job tracker, and it gives. Yes, that's correct, Rajesh. So copying the file can be done either using these tools, Scoop, Flume, or it could be done using simple HDFS client. There is a Hadoop client which help you copy single file or multiple file, while Scoop and Flume are for the production kind of settings where you have a lot of data. If you want to just copy couple of files, you will simply use Hadoop client, HDFS client. We'll talk about that. All right. Or you could use the browser to upload the files. Okay, I'll show you that part also. Now, the client talks to the job tracker, and then job tracker will start creating this diagram is a little wrong. Here, the job tracker will create the splits and then will start the work. Okay. Now here, okay, I think it's a Hadoop client which figures out how where the data available, and then gives that to job tracker, and job tracker then schedules it to the system. Now there's many things which job tracker does. The first thing the job tracker does is it goes to the job file, tries to understand what you are trying to execute. After that after that it will initialize the job. What does it mean by initializing a job? Creating a queue, marking that this section of the work has been given to this machine, this section of the work has been given to that machine, and once that is done, okay, once that is done, it gives the result back onto the HDFS. It saves the work back onto the HDFS. All right. Now, little bit more details on it. Job tracker creates something called maps and reduces. Okay. So maps and reduces the definition of the logic. When I said you as a client will be creating the code, you as a user will write the code what you need to execute on various task trackers. Okay. You as a user, what you want to execute on various task trackers on various computers containing the data, as well as if you want to summarize something, combine something, that logic also you will have to provide, right? So you will be giving two parts of logic. First, something called maps, that is a function you will write what to do with the block of the file. Okay. And your this function with the definition of a definition of a mapper which you will define, the definition of a mapper will be executed on all task trackers parallelly. All right. And the other part which you will define called reduce will only be executed on by default only on one computer. And reduce means you will, after the all the computation has happened, on all the machine, the data is gathered from all the machines, the output of all the maps, all the mappers has been gathered, and then it is passed through the reduce. Okay, so let's not jump ahead too much. So just for time being, you understand that you will be writing two parts of the logic. One is called map, other is called reduce. So now we have three things in the definition of our job. First was which file do you want to process? Second was what do you want to do on each node? That is called map. And how do you want to summarize the overall output? That is called reduce. So you are going to give three things to the job tracker: files, mapper, and reducer. All right. There are many more things. I'll keep adding to the list. more and more customization you want, you can keep, there will be more things you can do on MapReduce. All right. So, all right, don't worry, Johnny. I will, trust me, I'll be repeating it multiple times. Okay. For time being, you as a client, you want something to be done on all the nodes. And once it is done, what is it that you want to do after combining all of the output? Okay, so there are two parts of the logic which you will be providing. First is map that runs on each computer, each task tracker on top of the blocks of the file which you have specified. That block of the file will be the input to your map. Okay, so for right now, you can think of something called input is plate, which is on top of your block, a logical representation of your block. And that is what is fed to your mapper. Whatever logic you write, that will run on near each of the blocks. Each of the block is an input to your mapper. So parallelly, if you have 1,000 computers, the way I gave an example of Google, they ran the sorting example on 8,000 computers. So on all 8,000 computers, the logic of sorting happened. Okay. After that, the data was combined, and after the after combining all of the data, you might want to run some sort of processing further. That processing is called reduce. Okay. So why should client create the splits rather than job tracker based on the availability of the data in the node? We'll go into these details. Who does this job? These diagrams are not doing a little bit justice. We'll talk about it. So whenever we submit the job, it is the duty of the Hadoop itself. And when we say client, here client, this client means the Hadoop system itself. It's a Hadoop client. You are the user. You are this user. All right. Now, so hope I have cleared a little bit, Johnny. Even if you are not clear, don't worry. Do not panic. We will go into the more details slowly, slowly. I just jumped ahead to make sure that you have this curiosity right now. All right. So this is how the job tracker generally functions. All right. Now, again, let's look at the dynamics. So, Johnny, are you okay with my description or you want me to give more details right now? All right, good. Now, now same thing. We gave the work to job tracker. Job tracker assigned it to task trackers. This job tracker is monitoring these task trackers, checking whether they are executing the mappers properly or not. In case, and how is it, how this job tracker is trying to figure out how this job tracker is trying to figure out whether a task tracker is working or not by sending the heartbeats. So job tracker keeps on sending to the heartbeats to the task trackers and vice versa, and they keep on responding to job tracker saying I'm done this much, I'm done this much. So they keep on reporting the progress back to the job tracker, and in case a job tracker fails to respond for quite some time, or it fails to finish the job within a predefined time, then job tracker kills the task tracker and assigns it to somebody else. Kills the task tracker as in tells the task tracker that you don't need to work. Okay, and then whatever output it got from task tracker, it will ignore that output and instead it will assign it to somebody else. Let somebody else work on the same data. All right. That is how job tracker provides you a great resilience. Resilience as in, even if few machines go down during your processing, still you will get the output. It might get slowed down, but you will get the output. Okay. So job tracker gives you this kind of assurance that even if some nodes go down while processing, still you will get your results. Okay. The other way, a better way to think of the whole thing in this format. There is something called input split, which is created on top of every block of the data. Input split is the logical representation of the block. A block is a binary data. Input split is, say, few lines from my file. All right. Input split. Split 0 is first 500 lines. Split 1 is next 501 lines. And split 2 is next 510 lines. All right. So input split is created on top of the block of the data. That's a logical way of representing it. And then it is passed, that input split is passed through the maps. The map is your logic, and the map's duty is to give out the output, which has flag that sort my output with this particular key. Okay, so map gives out the output in the form of key value pair, and these this data, the values are sorted by the keys on each machine. All of these machines will be sorting the output of the map, and once the sorting is finished, the data is copied to another machine where the data from all these maps, the output of all these maps is merged into a single file and again sorted properly. Okay, it's again sorted properly. And after the sorting has finished, the key value pairs are passed through the reduce. Key and all the values for that key are passed through your reduce function and you get the result. And this magic of map and reduce can actually do everything your SQL query can do. Okay, it can do a lot of magic, although it sounds like very rudimentary right now. All right. Now, you might ask that what's the point of sorting on each individual node when you have to sort it anyway again, right? Here, let me go through from left to right. Here was your HDFS data. On top of HDFS, we created input split. Input split is the logical representation of your file, right? So we created input split 0 on top of block 0, block 1, block 2. Okay. Now this data is fed line by line or record by record. This data is fed record by record to your mapper, and your mapper converted that record into key value pairs. Mapper converted that record from each input split into key value pairs. Okay, because mapper wants this data to be sorted by that key. That's why mapper is something you write. It's your code. You will have to create key value pairs if you want to sort your data. All right, and based on that key, all the values are sorted and brought together, and after it has finished, the aggregation function in form of your reduce function happens. All right. Now you might ask, does anybody has this question that after merging, you anyway have to sort the data, then what's the point of sorting here, right? Or am I jumping too forward? Yes, the code for all the mappers, whether there are 10 mappers or 5,000 mappers, or it's a single mapper, the code is same. It's written by you in the form of, you can imagine that you can imagine the definition to be something like this. You can imagine the definition of your mapper something like this. Function, and it it returns, say, my mapper. This is my function. It takes the record, okay? It takes the record and it returns it say output dot send key 1 and key 2, okay? Key 1 and value 1, okay? It would do some magic. It will process record and create various key values. Okay, we will go into a couple of examples and we will make sure that you all understand how to write your map reduces, because it's not only the Hadoop that that map reduce matters. There are many systems as of today for which these map reduces matter. Therefore, we'll go into the details one step at a time. Okay, and like with any technology, you generally have to go a little bit back and forth. Okay, that is why I'll jump ahead and then come back and then explain again, so that we'll continue that. So this is the kind of thing you will be doing inside the mapper. Okay, and this logic will be sent to each of the here and it will be processing that. And once it is done, then merging would happen, and after merging it will be sent to the reduce. Okay. Yes, Rajesh, that is correct. If we have already sorted the data, merging a sorted data is easier. Okay, merging the sorted data is far easier than anything else. Okay. Now, Mark's question is, so does that mean I can have an input split for, say, split 1 HDFS store, split 2 Tomcat server with active listener, and third outside input? Or does it have, does it have to be, it has to be on the HDFS. The input split has to be on the HDFS. If you are trying to read the data from external systems, your mapper, your mapper is a Java code. Your mapper is a proper programming language code. If you're using streaming, then you can write in Python, which means your mapper can contact your Tomcat server, or any database. It can do anything you want to do. All right. But input split will be from HDFS. All right. Now, this was the map reduce where you have so many splits and we are running through this. But here my question to you was, we are sorting the data here and then we are merging it. Okay. So I'm saying that sorting sorting the merged data from various sorted inputs is easier. Meaning, if you're trying to merge the sorted data, it's easier to generate an output, right? Now imagine this. Imagine this. You had four queues, three queues in which people are standing by their heights. Okay? People are standing by their heights. So imagine these three queues. The one who is standing in front is shortest, then this person is taller than the previous one, and so on. Now, you are asked to merge these three queues into a single queue. You are asked to merge these three separate queues into a single queue in which the people would still be standing in order of their heights, in ascending order of their heights. Okay, the shorter one will be still in the front, and the taller one will be at the back. So if you are supposed to merge these three lines which have sorted which are already sorted, if you are supposed to merge, it's actually very easier than trying to sort the whole data again, right? And how do you do that? So you pick up the person in the front from all these three queues and take out the shortest one. okay, and put it into a new line, and then you compare the next three people, and then you put them into the new line. If they are, since they are all equal, so we are just putting all of them together. Now out of these three people, this person is shortest, so we take him and put it. Next will be this guy's turn, and then will be this, and after that we'll be just copy pasting all of it, right? So it was actually pretty straightforward and fast to merge sorted sorted input, right? So was this example clear? I merged three sorted inputs into a new input which is which is sorted, right? So I generated a sorted result by merging three already sorted data. All right. So that is what happens here. That is why the sorting is happening here. So map converted the records, the raw data into key value pairs that got sorted here. And after that, all the key value pairs generated by all the maps have come together and they have generated key and values. All the values for a key are brought together by virtue of this sorting, and then key and the values are passed through the reducer. Now reducer can do whatever it wants to do. All right. Now next mechanic. So we started with a simple thing where we gave our work to job tracker. Job tracker divided it onto the whole machinery of maps, and some magic happened there, and that magic was this. All right. So now the next step to is this reducer. Right now there is only one reducer. There could be two reducer as well. Alright. So your input split is fed to the mapper. Mapper generated key value pairs. Key Some of the keys went to one bucket and some of the key went to another bucket. The key in the first bucket were carried to the first reducer, and key in the second bucket were carried to the second reducer. Okay. So in case your reducer is too time consuming, if it's taking too much of time to process data here, you can further create multiple process. The way we have multiple maps here, we can also have multiple reduces. Okay. And how does that we can specify while we are launching our program. So we gave first thing we gave to Hadoop was that we want to process this particular file. Second we gave was a function called map, a logic of map, what is inside the mapper. That is what we gave it to. We gave it to Hadoop. Third is what is inside our reduce function, something that would combine the values for the key. And the key and values are produced by our mapper. Okay, from the raw data, our mapper produced key value pairs, and those were summarized by our own reduce function. Then you might say that what's the duty of Hadoop? Duty of Hadoop is sorting the data. All right. Now, okay. Now I'll come back to your question, Mark, in a second. And but that doesn't mean you don't write your question. Keep on writing your question. I'll answer at the end of the description. Now, we found out that one computer was not sufficient for executing our reduce. So what we did was we told Hadoop that can you please execute our reduce also on two computers? And and what did reduce do is what did Hadoop do for us is it created two reduces here. And because of that, the output of our map, the output, whatever our mapper was producing, the key value pairs, half of the key were put in one bucket and half of the key were kept in second bucket. And this happened on all the mappers. Now, the first bucket was carried to the first reducer, second bucket was carried to the second reducer. All right. So, there's a little madness happening here. So there are too much of data transport happening, and in case you increase the reduce further, you will see a lot more data to be transmitted. Right now it is 3 into 10, 2, which is 6 time. The data transport is happening 6 time in your network. If you have one more reducer, how many times do you think the data transport will happen? If you have 3 reducers, how many buckets will be there? Anyone? Right. So it will take 9, total number of 9 transfers, and the number of buckets. Perfect. 3 buckets is. Thank you, Sergio. And yeah. All right. Now, so this is the little magic which is happening over here. So your work got delegated on both the ends. The only thing is the reduce, when we send the work to the reduce, a single key will always go. A key, say, first mapper also generated a key called Sandeep. Second mapper also generated key called Sandeep. And third one also key call generated Sandeep. So Sandeep in all these three mappers will either always be in the same bucket, meaning if it is in the first bucket here, it will be in the first bucket here, in the first bucket here, and values of this key called Sandeep will be carried to the same reducer. Okay, it will be carried to the same reducer, meaning one particular key, no matter how many values are there and no matter how many mappers have generated, all those values will go to a single reducer. All right, no worries. If you are still not with me, it's okay. I'll explain it again. All right, so let me read Mark's question. So, so key 1 could be largest to smallest key, 2 smallest key to largest. Okay, key 1 could be largest to the smallest key, key 2. Oh, okay, I did not get this. Maybe. Okay, great, great. I already answered. Nice. And all right. Now Rajesh's question is given then each split will be input 1. Let me read it. Gi- Given that each split will be input to map 1, what happens when splits are for blocks in the same data nodes? Okay, that would mean one mapper will work on 2 input splits. That is correct. Okay, so Rajesh's question is what happens when there are multiple blocks on the same machine on which this mapper has to be executed. Okay, so there will be basically your input split will be prepared on top of multiple blocks. Okay, in those cases your input split will be prepared on top of multiple blocks and the data will be inputted to the map. All right. Now, okay, so Same diagram again, where now, so this was a story which was there. Everything was monolith. If you notice, there are two big things which are happening. First, the mechanics of job tracker and task tracker, where we are asking job tracker to execute something, it's executing those things on task tracker. That is one mechanics. That mechanics involves a lot of resource allocation. Figuring out what to execute where, that kind of mechanics is one part. Second part is the sorting way, where the the each of the task tracker will execute our mappers and will sort the data, collect it, and do the job. So these are two different things, and both the things were part of a single component called Hadoop MapReduce in 1.0. Okay, so these two things, one was MapReduce execution, MapReduce, this whole idea of MapReduce, and other was task tracker and job tracker. So if you think about it, job tracker, the way it executed our map task and reduce task, or it executed the MapReduce framework, it could execute other logic as well, right? That is the reason why Hadoop 1.0 was broken into two parts. Okay, in Hadoop 1.0, the resource allocation, the resource allocation part, the core, what to execute where, and if it is being executed, then is it happening in the right time or not? That kind of supervisor's role was split it out from Hadoop, from the whole MapReduce mechanism, and create something called Yarn was created. Yarn was created. So MapReduce was the resource allocation, resource management part of MapReduce was taken out and made a separate component called Yarn, so that other people as well, other kind of frameworks similar to MapReduce can also can also utilize the resource allocation done for MapReduce. Right? Now here you can see this. So the moment we have broken the MapReduce into two parts, one is called yarn, this side, and other is called MapReduce. Okay. Now whatever code you wrote for MapReduce in the form of MapReduce is still intact, because the MapReduce understand is still the same language, but it made a way for other people to build systems on top of Hadoop. All right. Now, by virtue of this modularization, by virtue of breaking monolith component called MapReduce into two bricks, one became the proper MapReduce framework, other became the resource management. Resource management opened the door for other new innovation, and because of that innovation, today we have things like Spark, which are running on Hadoop. Now you can see this. So MapReduce is just one component as of today. You have HBase, Storm, in-memory computation like Spark, and so many. Every day there is a new framework being created on top of Yarn. So Yarn made a way, Yarn democratized the process of executing the things, and so that lots of people could write their own logic. Hadoop was no longer limited to only MapReduce. MapReduce has its own limitation. So basically, Yarn supported more workloads other than MapReduce. Okay. Second was scalability. The MapReduce was not the Hadoop 1.0 was not fairly scalable. There were a lot of more optimizations done in Yarn in order to make it scalable. More and more, if you add more and more computers, you should scale up, scale very well. Those kind of optimizations were done in yarn framework. Third was compatibility with MapReduce. So whatever logic you wrote for your old MapReduce would still run. All you need to do is recompile it and upload it again, right? Now, fourth was improved cluster utilization, because the engineers who wrote Yarn, they kept on focusing on resource utilization rather than the whole framework in one go. They could basically focus a lot on optimization of resources. Agility, of course, because of the breaking down the monolith component into two parts, it made a way for lots of other things. And moreover, MapReduce was not sufficing for lot of use cases. MapReduce was batch oriented, meaning we gave the task to MapReduce and then we forgot. We had this faith that it will execute somehow. It has this resilience, it will keep trying, and once it is done, then it will let us know. But if we had to do something really, really immediately, and in case there's some failure, we need to just close everything. Those kind of scenarios were not catered by Hadoop. Okay, and that means by MapReduce, those were not catered. Okay, and that's why the next architecture was something little more complex. Job tracker, task tracker became something like this. The most closest definition of task tracker is now node manager, and most closest definition of job tracker is resource manager. Okay, and then application master is there. For MapReduce, there will be one application master. For other kind of application, there will be another application master, and then there are per node slaves of node manager. Okay, and per application container, make sure that application master does not cross its boundaries. So those are the many breakdown was done, and the diagram little looks little more complex. Now, task tracker, job tracker looks more like a resource manager in Yarn framework, the Hadoop 2.0. Okay, we can actually write here saying it is Hadoop 2.0, and all you can also do 2.x. Right now we are on 2.2. Uh-oh, I missed a lot of questions. So slide number 2. Yeah, this one is a good slide in the sense that it shows you a lot of this one. All right. So name node and data node remain as such. Name node and data node, HDFS was not touched in case of Hadoop 2.0. Other than minor optimizations, name node, data node remain same in Hadoop 2.0. Mark, this is the slide you wanted to see, right? All right. So any questions till now? Yep. All right. So the overall idea about these online training, live trainings, is that you can discuss the questions and get your questions answered. Okay. There are many videos here and there, and lots of things are there, but I mean, getting your question answered is probably the most important idea. And trust me, your question would be bothering, the question you might have in mind might be also bothering other people. So that would be helpful for all. Okay. In Hadoop 1.0, the name node and job tracker were on the same machine. Not really. Okay. So in any situation, the job tracker, they look same. And generally, this is the architecture, general architecture, but not necessarily. As long as job tracker knows where is the admin node, or As long as job tracker knows where the IP address of name node and the port number, job tracker is good. Okay, it doesn't have to be on the same machine. I'm trying to answer to Rajesh's question. Next time I'll repeat the question. All right, so here we are. Now this is how it looks like. Our task tracker sort of became node manager, job tracker became the resource manager, and for each new application we have application master running and a container. Okay, there's application master and there's a container, and these so for each of the application there will be this logic running for each one, talking to node manager, getting it executed there, and also container is ensuring that a container is also ensuring the communication between application master and others. Okay, so it's little complex here. We will also talk about in detail later on, but this is what happened in general. Okay, so per application framework was made possible here. And because of that, as of today, even Spark, you don't have to do anything to run Spark on top of Hadoop. All you need to tell Spark is, this is my name node, and that's all. Okay, this is my name node, and this is my uh, resource manager, and that's all. Rest of the things it takes care by itself. All right. Now, so a little hands-on. Here we have talked a lot about the whole mechanics. Okay, we will once we have gone through the code, once we have seen a script, how to create map, how to create reduce, then we'll go again into this architectural detail of Hadoop, and then we'll go ahead with other components. All right. Now let's see how does it look like. All right. Now we go ahead. So let's have a look at how does our Cloud Labs looks like. If you log in here, the details of the Cloud Labs and the installation instruction is available under My Courses. You go to My Courses and click on the course page. Under the session 1, you will see the installation instructions. Okay. In this, you will see the details, right? So these are the login passwords of our Ambari, and all right. And here, if you are really interested in installing locally, you can download a virtual box. Okay. And in case you are okay with using Cloud Labs, you can start using the Cloud Lab by opening this URL in the browser. Okay. Here it shows you that name node is up, secondary name node is stopped, data node is alive, all 4 out of 4. There are 4 data nodes here, meaning there are 4 machines. And also it shows you how many hosts are there. It shows that, let me clear the filters. It shows you there these 4 nodes. I'm using our cluster manager called Ambari. Ambari is also from Apache and actively developed in conjunction with Hortonworks. And here you can see that Yarn is there. Yarn shows that there is something called resource manager, there is something called node manager, and there are these clients. All right. Now, this is the administration UI. This is the administration UI, which shows you the various kinds of diagnostics on top of your whole network. Okay. And if you plan to install a cluster instead of a virtual machine, if you want to personally try it out, probably the easiest way To install your Hadoop cluster is by the way of Ambari. All you do is on one machine you install Ambari server, and on other machines you start installing Ambari agents, and rest of the things Ambari will take care. You can install whatever clients you want, you can install whatever servers you want. You do not have to go into any other configuration way. All right. You can see that here if I have to, let's say these are the services. Let me go into, say, hosts, and on each host, say Hadoop 1, hadoop1.nobigdata.com is one of the hosts. On this node you can stop start anything. Also, if you want to move, say there is a name node and you realize that this name node is insufficient, so what you do is you just click on this drop down and say move, and you can move it to another machine. Okay, so that kind of provisioning, administration, and even installation is extremely simple, right? Say for example on Hadoop 1 you want to add one region server or one node manager. You can immediately add these services. Okay, if we did not have these services, it will give you that option. All right, all you need to do is on one machine install Ambari server. So here I have installed Ambari server on Hadoop 1. On Hadoop 2, Hadoop 3, Hadoop 4, all I did was I installed Ambari agent, and then I came onto this dashboard. I said host and action and add new host. If I have to add more computers to my system, all I need to do is add host, and I give the host names, and then it will install. It will give me the option of what all services do you want to install on a node. Okay. It doesn't give you the option of installing Spark or Storm, but it gives you the other main components. Yes, Tim. So the Ambari is from Apache. If a Spark or Storm is on Hadoop, will it monitor them as well? Mm, it doesn't actually. They are developing it. They're developing plugin for Ambari. Probably next year. I mean, not this year itself. It will be out. So, but it basically helps you monitor almost all the components. Okay. You can also add more services here. All right. Okay. When we are on this topic of provisioning, so all we did was as a general step. So we had Hadoop 1, we bought Hadoop 1 first. We installed, we did nothing. We installed Ambari server on this. Yes, we can do that, yeah. So we installed on this one. Then we went to browser and we said go to Hadoop 1 dot no big data. Okay. These instructions are fairly straightforward. All you need to do is use the, I'm using CentOS. I did yum install Ambari server. Okay. I will actually, the reason I have not prepared this installation document is because installation demo, because it takes a little bit time to install things. Okay. I will instead prepare a video and share it with you. I'm anyway planning that out. So you install Ambari server on one of the machine. And once you have done that, you go to the browser, go to the browser and open this. Next is you basically go to hosts, go to hosts and add hosts. Okay, go to hosts and there you can say add new hosts. And in this you either can provide the host name. Okay, say I gave, let's say tomorrow we are buying another server, Hadoop 5. I can provide this. Initially, I just said Hadoop 1, Hadoop 2 dot no big data dot com, Hadoop 3, Hadoop 4, and so on. Okay, next is either you can provide your SSH key, you generate SSH key of newly bought server and then provide that public key so that this machine will talk to it and install Ambari agent by itself. You don't have to even install an Ambari agent on these machines. Okay, all you need to do is provide SSH key and that's all. It will do everything for you. Okay, and then you say register and confirm and then it will connect to that machine, install Ambari agent, as well as it will give you the confirmation as you can see in this diagram here, in this UI. The next steps are confirm the host, assign slaves and clients, and then do a little bit of configuration, review, and then start the installation. And then it will install everything. And that is how I install the Ambari server. So in case you planning to install the cluster like me, this will be the simple strategy for you. Okay. Because I have tried at least 5 6 different provisioning system. I've tried Cloudera, I've tried others, though those are very very clumsy. And then I talked to the people who were in the administration at InMobi with me when I was working, because InMobi has biggest uh, Hadoop machines. Okay, not biggest, but they have a decent number of Hadoop instances, and the administration team was good. So they told me that Ambari's Ambari is a good provisioning system, better than other ones. And then I found it really good. Okay. Because with Cloudera, it became a little bit clumsier to manage my server. Every time I have to go through a big loop. All right. And in case we want to remove a service, it's pretty straightforward. You just say that stop and then you can delete it. Similarly here, similarly, we can say stop and then decommission. All right. So the moment, a good demo would be that we install HDFS. We see that our file is stored on multiple machines. Then we shut down one data node and see if our file is also accessible. You should try it out sometime. All right, now that was the web interface of Ambari. Is anybody unmuted or something? All right, so that was Ambari. Now let's have a look at the other interface called Hue. So any questions till now? So all I described was you can use Ambari to install the cluster, and you can simply use a virtual machine kind of setup if you want to try once. And to connect to Ambari you need a browser. To connect to Hue you need a browser. Okay, just like this. Now here you have this is the HDFS. This is the Hadoop distributed file system installed on all different machines. It has got a nice UI. It feels like it's a normal file system. Okay, it looks like it's a normal file system. All right, so here you can upload the data. You can create new, you can upload files, zip file. If you upload zip file, it will automatically explode it into a folder. You can create a directory, you can create a file, and you can change the permissions here. Also you can move the data around. So this is Hue provides a way to interact with your Hadoop services. Okay, so file browser, HDFS file browser is one. Then you can talk to Hive. If you have SQL kind of queries to run, you can use Hive interface from here. You can use Pig interface from here. You can use say job browser from here. You can also create job Uzi jobs using this interface. Yes, Ambari sort of acts like Mesos, but I have not used Mesos. I would try Mesos, then I'll be in a position to. Okay. Ambari is more like Puppet. Do you know Puppet? Puppet is one very generic system of provisioning machines. Okay. If you are running your own cluster, you own a cluster, and other than Hadoop, if you want to install something else, probably a Puppet will be a better answer. Okay. But the way people do it generally is let Ambari manage all the services it can manage. For rest of the things, there is Puppet. All right. So the name is Puppet. Okay. You can look at Puppet. So this is the one, and it's doing pretty good. A lot of people use it. All right. So now you can interact with these services using Hue. Along with that, you can use SSH. Also, I forgot to tell you, here this is your file browser. Create your own folder. Do not fiddle with other people's work. Okay. I have kept the same login purposefully for all the people, although it's possible to create different accounts, but I've kept the same login for all so that you can sometimes you might want to see what other people are doing. Okay. I have no clue why it's called Hue. That was Johnny's question. So Johnny, you can send it to all so that I don't have to read it again. So I have no clue why it's called Hue, and I'll actually find it out. Let me note down. All right. So in this file browser, you create your own folder here. You can create something like new directory, and with your own login name, you can create here. And once you have done that, you upload all your data into that one and maintain a kind of a code of conduct that you don't fiddle with other people's work. Okay. Because it was becoming a little bit of more headache for lots of people to share the data between amongst themselves. That is why I thought, okay, let's just keep it same in a single login. All right. Here you can create your own folder. My data is lying in Asgiri folder. Okay. Here. All right. So there's a lot of data, lot of files, mostly related to this sessions exercises. And this is HDFS. So whether you uh, I mean, I'll show you from the command line as well. Now, the other way of connecting and seeing the cluster is using SSH. So, so how many of you are on Windows? Okay, okay. So I think I should have asked the other way around. How many of you are on Unix? So looks like everybody's on Windows. Okay. Now, for those who are on Windows, I'm guessing that you might be using something called Putty. You can use something called Putty and connect to our SSH server. Now you can say in Putty you specify the login as student and server name as Hadoop 1.no big data or Hadoop 2 on Hadoop 2.no big data. All right. And then you enter the password which we have been mentioned in that installation document. So they here after you log in, you can interact with the HDFS using a command called Hadoop FS. Okay, so if I say Hadoop FS minus ls, it will give me the directory listing of Hadoop. Okay. Now whether I am connected to Hadoop 1, so here I am connected to Hadoop 1. Let's say here I am connected to Hadoop 2. Okay. So after logging into Hadoop 1, I'm asking HDFS to give me the listing of the folder structure. Okay. And here, in case I'm logging into Hadoop 2, now the machine is different. This is a different computer. Here also, if I say Hadoop fs minus ls, it gives me the same directory structure what has been given on first one. It exactly same. You can see that this is the same. I'm onto the second terminal. Now I'm in the first terminal. So the folder structure is same. Everything is identical. Why? Because it's a central HDFS. Okay. All right. Now you can use command like mkdir to create your folder. Also, if you want to copy something from local machine, local machine, when I say, I'm talking about Hadoop 1 dot no big data. So when I say local machine, I'm talking about this machine called Hadoop 1. When I say here on the second terminal, when I say local machine, it's the local machine here. It's a totally different one. It has not much data here. Okay. So, so there are one is local machine, this one, the local file system. Here, if you see the PWD is different. And if I say PWD in HDFS, oh, it doesn't have PWD. All right. Yeah. So you can see that there is a local file system on each computer and there is a central file system called HDFS. Okay. And this HDFS is the same one what we discussed. It has got name node, it has got data node. Whenever we are executing any command, it is going, this is the client. When we talked about in our diagrams, when we talked about client, this is the client. Okay. This guy is, when you say fs minus ls, this guy is talking to name node, asking for the folder structure and displaying it. Okay. So anybody? So when we say Hadoop fs minus ls, will will it talk to data node also? Anyone? When we say Hadoop fs minus ls, will it talk to data nodes also? And why? Not really. It will talk to the name node directly because it is trying to get the only the metadata, not the real data. Right. It is only talking with admin node. Good. And when we say things like, let's say we want to see what's inside this file called textfile.txt, then we say fs cat and this file. Now, do you think it is talking to data nodes? Any data node? Did it talk to any data node? When we say show me what is inside testfile.txt, did it talk to any data node? Yes, you're right. So, Sarju, it's okay to send it to a whole audience. It's okay, completely okay. All right, great. So that's about, you know, and if you want to copy something from local directory, say we have got, let me try to copy this log file. I want to copy this log file into my folder. Let me go to my folder here. My folder is as Giri, and similarly we say Hadoop fs minus ls as Giri. So this folder is the same as what we have here. Okay. Here there is no pig log. Let me copy the pig log from local file system. We say Hadoop fs, then we say copy from local, and we give the file name and we say asgiri. Now it is copying this file from local machine onto this one. Now after I refresh it, you will see that it has copied the data here. Yes. All right. Now here you can see that it has been uploaded. Perfect. You can quickly see the data inside any file using this browser. I like this hue because it lets me read few blocks of the file, and you can also see the last block very quickly. Also, you can download the file and you can see the file location. All right. So we were able to copy the data from our local machine. Local, when I say local machine, it is Hadoop 2 right now. It's not my laptop. It's this Hadoop 2. Okay. Now, second thing what we want to do is we can also upload data using this. If I have to copy something directly onto HDFS, I'll actually use this browser. Okay, I'll just upload the file. Not this, I'll upload the file. Okay, if I have to upload something from a local machine, I'll just upload from here. Okay, so you can see that my events.csv, not this, sg word count, we can put, or let's say this paper on Mario. All right, so now I'm uploading my file from laptop directly to HDFS. If I had to use SSH for this, I will first copy using SCP, or you will use WinSCP from your laptop, and then you will copy to Hadoop 2 or Hadoop 1, and then from there you will use this command called Hadoop fs copy from local. Then that means you will have two steps. First, copy from your laptop to Hadoop 1, from Hadoop 1 to HDFS. Okay. If you use the browser Hue, you do that in a single step. All right. So we are able to upload. Did we upload something? I think we upload something. There was some Mario right here. Mario. Yeah, Mario PDF. All right. Here you can basically see it is downloading. Nevertheless, yeah. So we were able to upload this. Okay, so I think it's break time. Let's take a break and come back again. Where is the break? All right, let's take a break of 10 minutes. Back by 10:27 p.m. IST. Break for 10 minutes. All right, so we can start now. 3 4 minutes late today. All right. Yeah, you can. If you have more questions than what we are discussing here, you can drop them. You can send them to Hadoop at nobigdata.com. Okay, Hadoop at nobigdata.com. This is for the cases when you think that it will not be wise to ask the question in the session. So you can send them to Hadoop at no big data, but ask the questions as much as you can in this session itself. All right. Is everybody able to hear me clearly? All right. Now, these two things we'll not be touching today, but rest of the things we will. Now, let's try to do few things on the cluster. And okay, so we were able to do this, and let's move ahead. All right. So again, Hadoop one.nobigdata.com is the one which is having name node, and now the data node is also on 1 2 3 4. Okay. Also, the Ambari that manages our servers is located on this URL. Hue is on this. Okay. Note the last number. This is the port number. By default, if you do not specify the port number, it's considered 80 port for HTTP. All right. Now this we have already done. And WinSCP you can use to copy the files from local machine onto the cluster. All right. And if you want to move some file instead of copy, then you can use this command. Okay. And that file will be copied to the HDFS. All right. We have shown this also. So you create your own folder and put your work there. Okay. We will avoid this part. Instead, we will do this. All right. Now let's execute a MapReduce command. A MapReduce command is basically um, the default one is this here. So in a MapReduce command, you have Hadoop client the same as FS. Instead of FS, we are going to use jar, and this is the program. This is the like a zip file. In Java, you have jar, which contains the whole bundle of your project. Okay, in this jar, the examples that come with Hadoop MapReduce are packaged into one, and they contain all the information. It contains the information about which file do we want to process on the HDFS, and what is the map, what is the reducer. So let's try out the example, and we want to do word count only here. Okay, so anything after this jar file is the argument to this program. Okay, this jar file is a bundle of code which can read the argument also. All right. So Hadoop jar will execute the entry point of this jar file. This bundle will have an entry point, and that entry point will understand the argument being passed. Here we are passing one word called word count, meaning we are telling this the entry point of this jar that can you execute word count, and this is the input directory, and this is the output directory, meaning we will this word count will try to process this directory from hdfs, and will do the word count on top of it, and will save the result here. So let's first check what is there in this directory. Okay, say Hadoop. So we say Hadoop fs minus ls. So there is a big.txt in that. Okay, big.txt is Con Doyle's that Sherlock Holmes novels. It contains Sherlock Holmes novels, so you can see that. And so I'm saying cat and putting more so that I can see it page wise. Big.txt. All right. So you can see by Con Doyle, these are the Sherlock Holmes novels. I've downloaded it from Gutenberg. So we want to do the word count of this file using MapReduce. The code is already written and is shipped as part of the examples of Hadoop. We will be seeing the code later on, but for time being, you can have a look at it. Now here we want to store it in this folder, output there. Let's try to do it. Let's see what happens. Okay. It says the folder already exists. Now let's say we call it 8 March. Okay, meaning what we are saying is read the data from this folder, count the words, and save it in this folder. So now the important part here is it has started processing. It is trying to first connect to the resource manager. Okay, then trying to create the splits. Right now there is only one split because the file is hardly 10 MB, and it has created a URL for you to track what's going on with this file. Now, if you go to this URL, the same URL which is copied here, you can see that it again, I refreshed it. Now here it has finished very quickly. Okay, and it shows you that map this much percent finished and reduce this much percent finished, and quickly it gave you all the statistics about the map reduce process. Okay, so this is how it looks like. Okay, so you can go to job ID, and it shows that how many reduce are there. There is one map, one reduce, and on map this is what it shows. It shows you that there was one task that was succeeded. All right, and if you want to see further logs, you can see the further logs what went inside that. Okay, so we just basically ran a pre-coded, somebody has already coded the map reduce, and we just ran it using Hadoop jar command. All right, we don't need this. Yeah. All right, now here what does it say? Yeah, the examples are available there also. Now this is how you execute map reduce command. All right, so is it clear to everybody? You can try executing this command by yourself. It will give you an error. You create your own work output folder in your own folder. Okay, not in my folder. This is in my folder. Okay, don't create it in my folder. Input folder you can use mine, but output folder you should create in yours. Okay, run it and see the output. And if you want to see the output inside what has been generated, let's have a look at it. So we said store the output in this particular folder. Let's have a look at it. So if you have a look at it, how do you have a look at it? Hadoop fs minus ls, like this. So this is a folder. In this folder, MapReduce has created one 0 byte file called success, which signifies that MapReduce has finished successfully, and part one new file with a name called part 0000. If there are more reducers, these files, see, if there are two reducers, there will be two part files instead of one. Right now, there is only one file. And if there are three reducers, there will be three part files. Okay. Now let me see what's inside it. Okay. And how can I see that? By using the cat command or by using the hue. Now you can see that it has tried to do the word count, okay, but it hasn't done really neatly because the double quote is being counted as part of the word. The punctuation marks have not been removed in order to count the word. That is why indeed has come that many times. You see this? If we have to clean it up, we'll clean it up in the upcoming examples. But right now, this word count is what we have. All right, we counted the words using the predefined method, predefined example uh, in Hadoop. Okay. Now, what is so big deal about it? Right? It's just word count. We can also do it on the local machine. What's so big deal about it? What's the point? All right. Now let's have a look at it. So is everybody with me? All right. So now there is something we want to discuss a little more aggressive. We call it a thinking in map reduce kind of exercise. And this will go on for two more sessions. Okay. We will try to think in terms of map reduce and we'll try to understand how can we convert our problems into map reduce. All right. Now imagine this. Let's understand the essence of it. Let's say you have a plain text file. Imagine Lord of the Rings book, or what we have just done is all Sherlock Holmes volumes. Now if you have this big text file and you have to find out word counts, how many times the various words are occurring. If you have to do that, what will you do in without any Hadoop or anything? If somebody asks you right away, can you give me the word counts? Can count the words in this particular file? What will you do? Any approach. Any approach is fine. You just give your own approach. All you have to do is give in a big text file as in say maybe 10 MB, 5 MB, or maybe 20 MB. So given this kind of big file, all you have to do is tell me the word count of the unique words. What is the approach you are going to take? Any approach, any approach. Okay. Tim says dictionary hashet, good. And Johnny says look in the index to find the pages first. Okay. And then look at those pages. So let's say you don't have an index. You have just this plain text file. Sarju says that using ordering, okay. So elaborate a little bit. Elaborate a little bit. This will be. Rajesh says sort the entire text file, count the words. Good. Ordering and unique the data. Yeah. So meaning you will first pick up the words and then you will sort those words and then count the unique data. Great. Great. Insert pipes in between tabs and count in between pipes. Okay. Yeah. How would you do that? I want to know that. You could as well count the spaces, right? Spaces or tabs instead of before inserting pipe. If you do not insert pipes in between the thing, then also even without that, you can actually count the tabs, and that should be good enough. All right, Sarju's answer is little more specific. Good. You say cat file sort n and then unique. Great, but this file might contain multiple words in that file in each line, right? We want to cover do the word count for each word. And also, Mark, if the approach you are telling will basically count the total number of words, it will not tell me that how many times a particular word has occurred in this whole file. So the problem statement is find out the unique words in this file and tell me their counts. Okay. So if we do something like cat my file and then sort minus n, but will that work? Because what we want is one word per line in this case, right? But when you say cat file, one line will contain multiple words, right? Any other approach? You are right, Sarju, but just give me that little more detail. Y- You're correct. You're actually absolutely correct. Any other approach? There are multiple approaches. We'll go through multiple approaches. So one was hash chat. Okay, that is one. Second was okay. Johnny, what's your other approach? Other was sort the entire text, count the words. What Sarju is doing, and all right. So imagine this. This is a common thing which people do. Can you just give me the word count of this whole text file? Yes. So how would you list the unique words per page? So we don't have to do it per page. We have to do it for the whole file. Okay. Anand says use bucket sort. Good. Yes, we can do that. Yes, you can do that. And then list down all the approaches. There are a few more approaches. I'm waiting for those approaches. Will you use some sort of database? Will you use some sort of other approaches? You can try those. Maybe you could use Excel sheet. Okay, if you use MySQL with full text search, does that allow you to count the words. I don't know, I haven't used that. All right, perfect, perfect. So basically, yeah, that's correct. That's correct. Good, good. Both are correct approaches. Now moving on. All right. So, so we have three, four approaches. Perfect, perfect. And we will talk about these three, four approaches in upcoming discussion. Okay. So first one is if you have a plain text file, this is how we did in the beginning. So all we did was we created a dictionary, a data structure called hash table or dictionary, where we can insert key values in and is kept in memory. And inserting or retrieval from a dictionary or hash table is is actually a pretty fast operation. So we went through one word, each word in this file, inserting these words into dictionary if the word does not exist already, and if it already exists, if if a particular word already exists, then we just increase the count in the dictionary. And once we are done with reading the whole file, we just print what is there inside the dictionary. Basically, we created a dictionary of word as the key and counts as the value. For the first time, if a word is encountered, we just add that to the dictionary with the default value as 1. And in case the word is already existing in the dictionary, we increase that by 1. And we do it for all the words in this file. So, do you see any problem in this approach? This is the approach which we have been doing for quite some time. Do you think there is a problem with this? Yes? Perfect. So yes, as long as this dictionary fits into the RAM, it will be all right. Okay? RAM is a very precious resource. If you have 4 GB RAM and this dictionary is and this data is around 1 GB, so the dictionary size is generally 4 times the actual data. I'm talking about Python and Java. The actual storage taken by the dictionary is 4 times the key value pair size. And that's where the RAM becomes limitation, right? So as long as the data fits into the RAM, we are all happy. This approach is great. The moment the data becomes impossible to fit into the memory, this approach is absolutely useless. All right? Now, second approach, second approach is that we break the books into one word per line, as Rajesh and John have said, that you break down the whole text file such that there is one word per line, and insert that one word into one row in this database table. And at the end of it, you say select word, comma count from this table and group by the words. All right. And third approach is use the Unix. Okay. So what Sarju has said here, I'm making little bit more modifications to it. It's a here I'm saying cat file 1, file 2, how many file you are having, and then replace space or tab with the new line. That is first change, meaning I'm converting spaces into new line. I'm converting spaces to the new line, which means I'm converting this whole file into one word per line. Okay, I'm converting it to one word per line, and then I'm sorting it. So I'm using sort. Now there is this interesting parameter which I'm passing here. That is something which you need to look at it. This sort, there is a sort command itself gives you a parameter saying minus s1g, meaning it will only take 1 gigabyte of your RAM. It will not take more than 1 gigabyte of your RAM, and then it will use the bucket sort, as somebody was saying. So basically, it will, out of the whole data, it will automatically create buckets and it will load only 1 gigabyte at a time and sort it. And once whole data is sorted, then unique minus c will give you the frequency, of the characters. So how many of you are comfortable with Unix? Who is not comfortable with Unix pipes? Is it clear to you? No. This one? Be very open. I like to explain to you. Okay, no worries. No worries. So Rajesh needs an explanation, Santana needs an explanation, and okay. Good. So I think it would make sense if I describe it a little more. Okay. Now let's see. I will try to describe it a little more. So in Unix, you have these commands. You have these commands which can be piped together. Say, for example, a simple echo command, whatever command line argument. So first, first one is the actual command, and this one is the argument. Hi is the argument to echo. Okay. So whatever you write as an argument, echo just prints it onto the screen. Okay. This you can pipe to other commands. Okay, so for example, there is a command called word count. Whatever you type in the input, word command will just print the statistics about it. How many characters are there, how many lines are there, how many words are there, and so to these three numbers it will print quickly. If you do not pass any argument, it will take the data input from here. Okay, so we are just passing this and say control D, and say control D. It is taking from the standard input. If you do not, okay, so when we say this command, it is taking the input from me, and in case I'm putting pipe before it here, the data input is coming from left hand side to the right hand side. So echo, whatever echo is giving to the output, it is being sent to WC. Okay, so the data is flowing from left hand side to the right hand side. All right, and further you can pass, just for the fun sake, you can pass the argument output of WC to WC. Now it shows that there are three words. So WC is word count. It does number of lines, number of words, and number of characters. Okay, and here that is why we have one line, three, this has three words and 24 characters. It has included all the space. Okay, so WC, these are just few commands. Now let's have a look at, we can also put things like echo hello. Now we have two things, and we can combine the output together and we can say WC. Okay, it says that there are two lines in the input and there are two words and there are 9 characters. Okay, now we can pass the same input to sort command and it has sorted our data. All right, so from left hand side to right hand side we are basically piping our data. And then we can also say further, we can say pipe WC. Okay, and we can also say here, if we have two hellos, let's say echo hello, echo hi again. Okay, and you can see hi hello hi. And if you give it to a command called unique, and unique basically prints the unique words in the input. If you say unique minus C, it will count the unique occurrence. The only problem with unique is it wants the input to be sorted. Otherwise, it will give you the wrong result, like the way it has given you the wrong result. It, because unique does not sort. Unique, all unique does is it assumes the data is sorted and it only wants to count the unique occurrences. All right, now here you can see, that if we say sort, then hi will come together and then we can say unique minus C. Now you can see the count of hi is 2, hello is 1. All right, and if we put one more here, one more say hello, you can see now there are 2. It has quickly counted the results. Okay, so this is our input, and unique sort converted into sorted data and unique counted it. Okay, so we are piping the data from left to right. Okay, the output of one command is becoming the input of another, and so on. Sounds good? Sounds good. So if you had a text saying if you want to print one file, so let me see if I have another file. Otherwise I will just take the data from, let's say, all right, let me just see what is there inside this folder. Let me download the data from Hadoop itself. Hadoop fs minus ls and sgiri, then word count, then input. All right, it has some data. Now let's copy it locally just for the testing purpose. It's taking a little more time. All right, now here there is a command called sed. Sed basically replaces a word with another word. Okay, and those of you who have, okay, let me try to copy it. So I'm copying this data from HDFS to locally. Now you can see the big.txt has come here. If I say big.txt, and you can see the words. All right, now let's pick one line out of it. Let's take this line, and we say echo this line. It just prints this line, and then we break down, we substitute spaces with new line. Okay, we are replacing, like in your editor you see control F and you replace everything. Similarly, we are using a sed command which basically replaced spaces with the new line. Do you see this? All right, now the next thing we are going to do is we are going to we are going to now further, as a next step, we are going to translate everything which is capital into everything which is small. Okay, so tr command did that. We are piping data from left hand side, starting with echo. We gave it to sed, which replaced one word with another, which is replaced space with a new line, and next thing we did was translated capitals into lower. Now we have this. All right, now we pass this input to sort, and then we say unique minus c. So only this has come twice, rest of the words have only come once. Okay, sounds good to you? So this Unix command does a lot of things for us. Okay, if you are not comfortable with the regular expression, this is a regular expression which says space or tab and multiple times any of this space or tab and minimum ones. You should you should try to look at the regular expression session which is there in the session 1 videos. In the session 1 videos you should see regular expression session. It'll just take 1 hour and you should be able to understand everything. Okay, so this way you can do the replacing of the spaces with new line and so on. All right, so this is third approach. Now my question to you is, so was this Unix thing okay with you, or do you still feel that it's a little too complicated for you? Okay, all right. It's very important to learn this part. I always emphasize on generally understanding the Unix command line flow because that plays a very, very big role in most of the data engineering. Almost everywhere where is the data engineering, the Unix commands are being used uh, exhaustively. All right. Now, my question to you is we saw two approaches. One was the SQL approach, and second was the Unix approach. In this Unix approach, it says that only utilize 1 GB of memory. Okay, so both these approaches solve the problem which was raised in the approach number one, and that problem was the RAM limitation. So the RAM limitation problem was not something that impacted approach 2 or approach 3 because both of these approaches are fairly sensitive to RAM. Now, my question to you is, do you see the problem with approach 2 and approach 3? Yes, time consumption. And do you see any problem with approach 2 and approach 3? One is time consumption, that is good. Anything else do you see the limitation of approach 2 or approach 3? Scalability, yes. Meaning, what does it mean by scalability? In case the data is growing bigger, okay? The data is going bigger, not only the CPU going to take time. Read file taking long time. Exactly. So the IO, the input and output, the file read time will be too high because the hard disks are slower. Okay. So when you read the data, if you are churning few gigabytes, it might take maybe half an hour, or not half an hour, it might take few minutes. All right. So, all right. Now, okay. So the CPU will be one limitation. Other limitation will be disk speed. Other limitation will be disk space. We are all happy as long as the file is stored locally. In case the file is too big and we have made parts of it, one part existing on one machine, other part existing on another machine, these two approaches will not be able to process that kind of data. All right. These two approaches will not be suitable for we require more CPU, we require more IO, and in case our files are existing in the network will become the block. Now, so to overcome these limitations of the approach, what we did was we designed a system. What it does is we designed our program ourselves, and what it does is there is a computer or called launcher. From this, it sends the code to it brings the data from machine 1 and machine 2. Okay, let me repeat. So in this approach we are trying to use something called external short. We take our data, we send one part to one machine, we send another part to another machine, and from both these machines we get the frequency computation done, and then we merge them together and give the result. Okay, there is a machine called launcher. From this we sent the data to machine 1, and machine 1 did exactly what our Unix command was doing. Same way machine 2 did exactly what our Unix command was doing and gave us the computation of frequencies in those parts of data which have been given to machine 1 and machine 2, and then we combine the results given by the two and we give these results. All right, merging the sorted data into an output. And those who are wondering how will you merge this data, you can actually use the minus m flag of the sort command. Okay, sort command gives you minus m flag, which basically merges the already sorted data sets. All right, so do you see a problem here? How to split the files? Okay, you can split the file just like that. You can just take first 50 lines and then in one and second one and give it back, or you can use a command called split provided by Unix to you. So either way you can split the files. Now do you see a problem in this approach? If some process fails, it is hard to get the final result. Excellent point, Anand. And Sarju says more machine. Yes, that is one thing. But that is something we can't get away with. We need more machine anyway. Any other problem do you see? So from one machine, we transferred the data to machine one, and we transferred the data to machine two, and then machine one and machine two did the computation as in approach number three, and whatever results we got from these two, we merged it and we give the result. The client, the launcher has to know where the files are. That is correct. Launcher is we. We have a command. We have the command prompt. We are using a command called SSH. And for those who are wondering, so in case of a network, if you have SSH, so you can do cool things like SSH Hadoop 1 dot no big data dot com, and then we can execute any command from here onto that server. Okay, can see that. So from locally, I can execute any command on any server. More bandwidth for more distributed computation. Excellent point. Yes. So those are few problems. One is time consumption in transport of the data. The bandwidth consumption is too high because we are transmitting the data. For each requirement, we need to program this special purpose program, a special purpose script. And then, as somebody was saying, as Anand was saying, that in case one node fails, we have to transfer the load to another, and so on. So, in those cases, the workload distribution and all of that requires a lot of engineering. It requires a lot of engineering from the developer perspective. Okay, to be able to handle these kind of circumstances. Okay, so the solution is to use MapReduce to save these to avoid these kind of things. Okay, so few engineers actually thought about it, and that's why they built MapReduce, so that you don't have to transfer the data. Data is already lying in HDFS, and it doesn't require much of an engineering because the most of the complexity is absorbed by yarn and MapReduce for you. Okay, so all right, now again, what is MapReduce? MapReduce is a programming paradigm that helps you solve big data problems, specifically sorting intensive jobs. You would have to code two functions, mapper and reducer. Mapper converts input into key and value pairs, and reducer aggregates all values for a key. Okay? And MapReduce is not only specific to Hadoop, it is being used by MongoDB, CouchDB, and even similar kind of model is also being used by Apache Spark. Okay, so it's important to learn the mechanics of it. Mapper and reducer both can be written in Java, Shell, Python, or any binary, any program you want to can execute from the command line. You can use that as the mapper and reducer as long as it gives the key, correct key value. Okay, Now, let's have a look at it. A little dynamics about word count problem. Let's say how will MapReduce solve our word count problem? Word count as in we are given a plain text file, we want to do the word counts. Okay? Now imagine this, our plain text file looks like this. Okay? And this is converted into something of this sort by Mapper. Mapper converted into the word as the key and one as the value. Okay, so basically what Mapper did was it broke down into one word, it broke down into each word, comma, each word as the key and value as one for all the words in the input. Then after that, Hadoop takes up the output given by a mapper and forms the key and values. Okay, it sorts the data. Hadoop sorted the data. It brought ga up, ray, and then sa, and all the values which has sa as the key, it brought them together, 1 comma 1. Right, had there been one more ga, it could have one more ga here. Okay, now so you can see clearly this dashed line is what is represented as the transformation done by Hadoop to your data. Mapper Mapper was fed the input file. Mapper is your program where you have written this code that converts the input lines into key value pairs. Okay. And Hadoop has taken the data spit out by Mapper into key and array of values for that key. Now, what to do with this array of the keys, array of the values? What to do with array of the values is decided by reduce. Reduce is applied on each key and its values. Each key and its values. So, reduce will get one argument called key and another argument called all the values for that key. And reduce in our case, all we reduce has done here is summed up the frequency array, meaning it will return 1 in this case, 1 in this case, and 2 in this case. That's all. Okay. So this is the code written by us, this one and this one. Okay. And we gave it to Hadoop saying, can you please execute these map reduces? And we also told this is the file name. And we have uploaded that into HDFS. Now Hadoop took that file, fed the data line by line to our mapper. Mapper converted each line into words and keys and values. Okay, word is the key and the value is 1. And Hadoop took the output of mapper and sorted it. And then after sorting, it grouped the keys. It grouped all the values for a key, and after grouping it passed key and its values through our reduce function so that we can decide what to do with the keys, and then we get the output. So this is clear to everyone? Great, great. So basically Hadoop has solved our problem of sorting the data. Hadoop has solved our word count problem by the way of MapReduce. MapStep does sort and group but does not count. Right. So sorting and grouping is the duty of Hadoop framework. Our duty is only forming the key on the basis of which Hadoop will sort your data. Sorting and grouping is the duty of Hadoop. Our duty is only telling the Hadoop that this is the key on which our data has to be sorted and grouped. Yes, map lays it out so that reduce can do something with or without it. Yeah, all right. Now the same thing what happens in case there are multiple mappers in the network. Our file is located on two nodes, node 1 and node 2. Okay. Now same function will be replicated on both the nodes, and this is what is happening on multiple nodes parallelly. On first node you have this data, and on second node you have saresa, and here I have taken this simple saresa sarega so that I can quickly pronounce it, and also it takes less space on the screen. All right. Now now here the same process, our map was applied onto this data, and this converted our line into key value pairs. Our key value pairs are this. You can see this. In the first case you have the key value pairs here and key value pairs here. This second, you see the label second. So here the this is what it is. Our map has generated this, and map 2 has generated this. And after sorting, this would look like this. And after sorting, this will also get sorted. Ray has come up. All right. And after that, shuffling and merging would happen, and we would have a single place. You see, the shuffling happened and merging happened here after sorting. So we have this. At before reduce, this is what we have. For ga there is only one value. For ray there are two values. For sa there are four values. All right, and then we apply reduce on this data, and we get this. Make sense to you? All right. All right. So this is the case of multiple mappers. This previous one was single mapper. This is multiple mappers. And in the similar spirit is multiple reduces. The only thing we should note is each reduce will get the same key. Okay. So after the merging shuffling has happened, all the keys will go to one for all the values for a key will go only to one reduce. It would never happen that one ray went to this and other ray went to this. Okay, therefore both the ray will go to reduce, and similarly all the SARs have gone into the second one. Okay, that is most important part to understand. All the values for a key, no matter how many reduces are there, all the values for a key will be given to your reduce function. Okay, all right. The other way to think about map reduce is thinking in terms of group by. Okay, group by looks like very closely to our map reduce. The way when we said group by, we specify that this is my table, and here we specify that this is my file. In case of map reduce, we specify that this is my file, and then we say in as part of map that this is my key and this is my value. Okay, and that is like specifying group by keyword, and after that we specify that this is our aggregation function. and this aggregation function is something which is equivalent to the reduce, because the aggregation function knows what to do with the multiple values for this key. For this key, there would be multiple values. What needs to be done on them? How those values need to be aggregated? That is what is decided by an aggregation function, and which is equivalent of the reduce. Okay. Now that is pretty much about MapReduce. Okay. Now what I want to do is, these are theoretical questions and they will become the practical questions. Okay, so first question to you is, instead of word frequencies, instead of counting words, if we had to count frequency of characters, do you think it makes sense to use MapReduce? Okay, just think about it and let's discuss it on next Saturday. Go through these exercises. These exercises are also available in the in our course page here. Finish the quiz. Finish the quiz. You cannot finish the whole quiz. Second is, finish the subjective questions. Okay, go through these subjective questions. If there is doubt, just drop me an email at hadoop@nobigdata.com, hadoop@nobigdata.com, and then I will respond to you and answer your questions. Okay, so go through these problems. If you want, I can also describe it. Basically, first one is about counting the characters. Second one is about finding anagram in the Hughes text. Okay, like in this, cat, tact, and act are anagrams of each other, even though these don't make any dictionary word, but it exists in the input. So you have to print out anagram in the text, okay, using MapReduce. Second, third is, given a DNA sequence of people, you have to bring together all the people who have the same DNA. Okay, you are given a file which contains user ID space DNA, and you have to find out all the people who have the same DNA. Now the next question is, a file contain same file, but this time some researchers said, can you please get me all the people together whose DNA is either identical or whose DNA is or a mirror image of each other. For example, user 1, user 2, and user 4. User 1 has ACGT, user 4 is ACGT, user 2 is exactly mirror image of ACGT, which is TGCA. Okay, so you have to bring together such people using MapReduce. All right. Fourth is, this is little tricky question. You think about this. You are given who in this democracy, people are voting for each other. Voter one has voted for somebody, and so on. And here the richer's vote matters more than the poor person's vote. Okay, so the one who is voted by rich person wins as compared to the one who is voted by poor people. Okay, so you are given the bank account details of all the people who have voted. Now you have to find out how many votes each person got. Okay, for example, C was voted by A and B. Okay, and the worth of A is 5, B is 1. Therefore the C's vote count is 5 plus 1. F was voted by C and C's worth is 11. So F's vote count is 11, while A and B got 0 votes. Therefore their vote count is 0. All right, you given this list 1 and list 2, you have to find out the vote counts, and both list 1 and list 2 contains a billion records. All right, so given the billion records in both, you have to find out the vote counts. All right, so Work on this, and let's meet on next Saturday and finish these problems. By the time finish by that time, put in your own solutions to these four problems, and we'll discuss in detail further. All right. Are these problems clear to you? All right then. Okay. So work on these four problems and see you on next Saturday. All right. Bye bye. Have a great day.